Welcome to the Problems Channel Season 3, Episode 3, the episode which I titled One Telescope, Two Telescopes, because in this episode we will evaluate a certain finite trigonometric sum by exposing its underlying telescopic nature. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most benefit for yourself academically by working with the material presented on this channel is to go to the homepage of this channel, and at the top of the page, in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means please do ask. I will do my best to find the time to answer all of your questions. Across this episode and the following two episodes, we will come face to face with the idea that fixing a certain problem in mathematics, theoretical physics, or computer science, and then trying to generate as many distinct enough solutions of that problem as you can muster should be an integral part of studying and doing mathematics, theoretical physics, and computer science. And in this episode, we will look at the first way to evaluate the following finite trigonometric sum, or a way to compress, if you will, this here finite sum into a product. In this episode, I will present my algebraic solution of this problem that is based on nothing more than a few trigonometric identities at the middle school level. And that is why I branched out this original problem S3E3, the problem in mathematics, into three distinct problems, three distinct solutions in three distinct episodes, because I want to keep each episode manageable time-wise. As such, in this episode, I will present my algebraic solution of this problem using a few trigonometric identities and nothing more than the middle school arithmetic, basically. In the next episode, under the guise of the problem S3M3, I will also present my algebraic solution, but that solution will be based on the machinery of complex numbers. We will see how things work once we switch from real to complex numbers. And in the following episode, under the guise of the problem S3M4, I will present my solution of this problem that is based on synthetic geometry. And that is why I split this originally one problem into three problems, three episodes. It is best for you guys to watch all three episodes as a transaction and perceive this problem as a transaction. If you have any other ways to deduce what we're about to deduce, then by all means share your idea with us in the comment section under any episode. As such, in this mathematical problem overall, we'll look for at least three distinct enough solutions of the problem S3M02, or three distinct enough ways to evaluate a certain finite trigonometric sum, or maybe as a hint, a way to compress that finite sum of trigonometric functions of cosine evaluated at certain arguments into a product. And here is a little bit of the theory which we will need in order to expose the fact that if the sum is shaken a little bit, it can be turned into a sum that possesses a technically advantageous property known as telescopicity. So what is a telescopic sum or a telescopic series? In general, let's say we have a sum. Let's say we have a sum. It doesn't have to be finite, but the sum could be also infinite. But when the sum is infinite, we have to deal with other issues that will just obscure the main idea. So to keep things as simple as possible, but not simpler, the most straightforward way, we'll assume that our sum is finite. So it can be represented as follows. Let's say the sum of terms uppercase AK, where K varies from 0 to N, for example, and N is a whole non-negative number. Let us assume for a moment that that sum, and if we spell it out a little bit, it will run like this: a sub 0, a sub 1, plus a sub 2, plus so on, and plus the last, so to speak, term, an. There are many different ways in which such sums can be evaluated, and we look at some of these ways in the future too. For example, one way to evaluate sums like this is to borrow the idea of double counting from combinatorial analysis, and I will show the mechanics of double counting as it applies to finite sums like this. But here we want to expose the fact that underneath the given finite sum of the values of the trigonometric function of cosine, whose arguments actually form an arithmetic progression, there sits a series that is telescopic in nature. So let us assume that all the elements of the given sum can be somehow transformed into the following shape. And that magic transformation I will depict with the sign like this. In physics, this is approximate. In mathematics, it can also mean different things. But here we want to portray the fact that the elements, the original elements of our finite sum, are transformed somehow into the shape that is represented by the difference. Again, that difference can be different in different cases, and one but not the only such case is, let's say, it can be represented as follows: ak plus 1 minus ak. Let's say it so happens that it is possible to look at the structure. Usually all the information that we have is packed into the structure of the summand, so by looking at the structure of the summand, we can sometimes perform this transformation depicted with these two squigglies over here and represent each summand like this. So let us write down the few terms, the first few terms of that sum that will be represented that way. So the original term a0 can be represented which way? It will be a1 minus a0. The sum a1 can be represented then as a2 minus a1. The term a2 will be represented as what? a3 minus a2, and so on. And the last term of our sum can be represented as an plus 1 minus an. Again, this is just one way. It's not the only way. This is just one way to set up the definition of a sum that is telescopic. If it is possible to somehow transform each and every term of a given sum into the difference that looks, for example, like this. This is not the only way, but one way, a way. Then we will see that as we sum, let's say we put the plus sign on this side over here, you guys understand what's going on. So as we sum all the terms, what do we see happening? Let me take the red chalk. We will see that in such a sum, we will have like terms with the opposite signs. For example, here, a1 with the plus sign and a1 with the minus sign. These terms cancel out like this. Next, the term a2 and another a2 with the minus sign with the plus sign. These two terms cancel out, and so on. the term a3 will cancel out with the negative a3 and so on. Eventually, this term will also cancel out. And when we sum all these terms, then eventually, let's put the squiggly like this, we sum. And then if we sum these terms and experience the perfect storm of cancellations, if you will, we will see that the bulk of the intermediate terms in the transformed, in a slightly, or maybe not so slightly, transformed or modified terms with depicted with the lowercase a, k plus 1, and a, k, they cancel out or telescope in. And perhaps, I'll be honest with you guys, I did not make any research, but it's just natural to think that once the like terms with opposite signs in bulk cancel out, then what do we have? We have only two terms, that two modified terms of our sum that survive that perfect storm of cancellations. And what do we have left? We will have left a n plus 1, and here will be a minus a 0. Then in that case, the synonym or an alternative expression for that sum will look as follows. It will be a n plus 1 minus a 0, and to this type of results we usually refer as a closed form formula. And the more you study mathematics, the more you will realize that it's not really that straightforward to define what a closed form formula is in such a way that all the mathematicians in the room will agree exactly on that definition. But that's a small side technical wrinkle. And here, as you listen to this explanation right about now, you're probably thinking, Roman, what is this transformation? What hides behind this? How do we find what exactly that transformation is, and what are these mysterious lowercase symbols, lowercase a, k plus 1, and ak? This is a good question. In general, the type of transformation that may lead to this representation of the terms of the given sum as this type of difference depends a lot, and pretty much all the time, on the structure of the sums, because in vacuum, when we rip out the sum out of context completely, we do not know what surrounded this sum a few seconds ago, and someone gives it to us and says evaluate. There is pretty much no information to go on except on the fact that we have the sum that is finite, and then the structure of the sums is all the information that we have, and that is what we key off of. So each specific transformation that may allow this type of presentation of the given term of the given sum depends a lot on the sum itself or on the structure of the terms. And then consequently, these two guys, the lowercase a, k plus 1, and ak, the exact shape of these modified terms, if you will, or modified sums, also depends on the structure of the terms of the given sum and on the chosen transformation. And again, it sometimes so happens that this type of transformation can be carried out in complete vacuum just by looking at the shape or the structure of these terms without invoking or bringing in anything else. Sometimes it seems impossible. Okay, and in the first case, if the first case is possible, if we can look at the terms of the given sum and say, hey, we can represent these terms like this just naturally, then we can agree that the underlying sum is called telescopic, or maybe we can say naturally telescopic, where we can perform this manipulation by using nothing else but the structure of the summons itself. Sometimes such a sum does not seem to be naturally telescopic. In other words, it's not obvious how we can take the given terms and represent them as the difference in a meaningful way. Of course, we can throw all sorts of zeros or plus 1, minus 1, but that will not help. So in that case, if we cannot do that, and in this sum that we're dealing with, the finite sum of cosines whose arguments are in a arithmetic progression, it is not entirely obvious how to represent it that way, then we can perhaps call that sum not naturally telescopic. But sometimes it so happens that if we shake that sum a little bit, perform a certain transformation with this sum and its summons, then we can elicit the fact or transform or morph that sum into a sum that is telescopic, and then we can achieve the goal, find an alternative expression for that sum, or what many people refer to as a closed form formula. Now, in this representation, look at this. If we were to write down the first few summands of our sum in the modified form, we will have what? A1 minus A0 plus A2 minus A1 plus A3 minus A2, and so on. So let's say, for example, what is the distance between the like terms with the opposite signs? Well, here the distance is 2, because A1, the term A1 over here with the plus sign will cancel out with the term A1 with the minus sign. These two terms will cancel out. And what's the difference, the distance between them? 2. So the distance between like terms with opposite signs is 2. But again, this is not the way. This is just a way, one type of representation. And depending on the structure of the summand, if such a representation is at all possible, then the distance between the like terms with the opposite signs may be less than 2 or more than 2. Sometimes this dance of like terms with opposite signs gets quite elaborate. They're stretched further apart. There is more material between them, but still they cancel out. It may so happen that not just 2, in this case, in our happy demonstration case, there are only 2 summands left. We refer to this 2 summands over here as a closed form formula, exactly. And in case when there are more terms survive this perfect storm of cancellations, we still refer to the result as the closed form formula. And now, in order to understand how this telescopic sums work, let us look at a concrete example. In the previous segment, we defined a sum to be telescopic if each and every term of that sum can be represented as a difference in such a way that the bulk of the intermediate modified terms cancel out, and whatever terms or whatever material does survive that cancellation process is what we refer to as the closed form formula for that sum. But here is a fun fact about exposing telescopicity or exposing the underlying telescopicity of such sums in particular, or the fact about evaluation of sums in general, or evaluation of products in general. As far as I'm aware, there does not exist an etched in stone algorithm in mathematics in which we input the shape of our sum or a product and out pops all the possible ways to evaluate such a sum. In other words, the process of evaluating a given sum or a given product is an open-ended process or is an open-ended problem, and that is precisely why we do this type of problems on our channel, because in general, in mathematics, theoretical physics, and computer science, this is precisely what you will take on eventually, an open-ended problem, and create the future non-existent yet textbook knowledge, if you will. As such, in each specific case, we are pretty much on the hook to expose and exhibit our technical creativity, ingenuity, and improvisational skills, and discover which specific transformation may put the terms of a given sum into a shape that is telescopic, or in this specific case, we need to find a way to evaluate a given sum, and we will do that many times on this channel. We will integrate, differentiate, construct systems of differential equations, and what have you, and we'll do all sorts of wonderful things. But here we want to understand, look at a concrete, specific, and clear-cut, understandable by everyone example of a sum that is telescopic, perhaps middle school or even lower level. So let's say perhaps the most popular example of a sum that is telescopic is the sum of the reciprocal products of two consecutive whole, let's say, positive numbers. So this is our sum that looks like a reciprocal product of two consecutive whole and positive numbers. Evidently, that sum will run from 1 to n. And the question is, for example, what is an alternative expression? What is a synonym? Or, as many people refer to it, what is a closed form formula for this expression? Even to some extent, playing the devil's advocate, we have all the information that we need in order to produce the result of this here. In this case, well, mathematical object in general or an arithmetic expression. So if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, boom. 14 symbols all are in front of our face. There is no mystery over here. Just go at it. Do step by step what this expression is telling us to do, and voila, we have it. So why is this better than anything else that can be represented by this thing in a different way? But so what is going on with this finite sum, and why is this sum, let's say, naturally telescopic? Well, here is the magic, the way things work. So this term over here from our previous segment is what we can refer to as uppercase AK. Remember, so here uppercase AK looks as follows: 1 over k times k plus 1. So that much is a straightforward example, specific concrete example of our abstract term from the previous segment. By looking at the structure of this specific sum, what can we say? Yes, definitely we can say that we can, for example, represent that reciprocal product, decompose that product into partial fractions, what we refer to as partial fractions. And what will this partial fraction look like? Well, if we put 1 over k minus 1 over k plus 1, once you do this type of problems a lot, you will pretty much know what the partial fraction decomposition is. I will not go into all the details, even we can do it formally with the coefficients, equations, and all that. But here the example is straightforward, so we can represent it as which way? K plus 1 minus k divided by k times k plus 1. Once we bring everything under one denominator, positive k and negative cancel each other out, and voila, we have our original term. So in this case, the miraculous or mysterious transformation that I designated with squigglies in the previous segment looks like what? This is exactly what it is. You see, in this case, the squiggly stands for partial fractions decomposition. And what is this then? What is this guy? Well, this is our a k in this case. And what is this? Well, this is our a k plus 1, because in general, this is what it is. Let's write it down perhaps officially. A k is equal to 1 over k, where k varies from 1 to n. And in this case, what can we say about this sum right here? What is the idea behind this transformation and this expression representing our each and every, as we remember from the definition of a telescopic sum, each representation of each and every term of a given sum as the difference of two terms. In other words, here we represent, let me write it down here so you guys can see it explicitly. In this case, this will be what? AK minus AK plus 1. You see, in this case, we swapped our terms around. It doesn't matter. This is what it is. Sometimes the expression can be more elaborate. There could be different material baked into this representation, but essentially that what it has to be. It has to boil down to things that will cancel in bulk when they're put together. So once this is understood, let us carry out a few computations. Spell out the sum with this observation that we just made. So here we will have each and every, remember that AK, I will write down over here, is 1 over K minus 1 over K plus 1. So for the first summand, what we will write? 1 over 1 minus 1 over 2 plus. So this represents the term A1. What will be the term A2? Well, it will be 1 over 2 minus 1 over 3. See, this is the term A2. You see, this is how things work. By this formula, we simply write things down. Plus, the third term will be 1 over 3 minus 1 over 4. You see, this is our term A3. Plus 1 over 4 minus 1 over 5. And this term will be A4, and so on. Plus, it will be what? 1 over n, 1 over n minus 1 over n plus 1. This will be the term an. And what do we see now? Well, in this case, remember, in the previous segment, because of a way in which I represented each and every summand as the difference, the distance term-wise between like modified terms with opposite signs was 2 elements or 2 terms, 2 modified summands. And in this case, what is this distance? It is 0. Such like terms with the opposite signs are jammed right against each other. In order to make it painfully clear, let's do this. Let's cancel it, negative 1/2 and positive 1/2. Now next, negative 1/3 and positive 1/3. Negative 1/4, positive 1/4. Negative 1/5 and positive 1/5 will cancel out. Eventually, this will cancel out. And what does that mean? Well, when that happens, we know according to our definition, that means that the sum presented over here telescopes in, all the terms telescope in or get canceled out. And what do we have for our closed form expression, if you will? Well, we will have 1 minus 1 over n plus 1, or another way we will write it down is which way? N over n plus 1. You see, and again, because by looking at the structure of the given summand, of the common term of the given sum, we realize that the mysterious transformation that puts our each and every term into a difference in such a way that the bulk of the modified terms cancel out, the sum is what? The sum is telescopic. We did not really, for example, multiply both sides of the sum by some clever function. We did not do any other transformations. We can say that this here sum is naturally telescopic. And once that is understood, that is how things work. Again, I want to make sure that everyone in the audience understands that the transformation that may lead to a representation of each and every common term of the given sum as an advantageous difference that works in such a way that when these terms are summed together, the bulk of the material cancels out, is not really known ahead of time. As far as I'm aware, there is no one single etched in stone rule which says, look at the term, do this, and voila, you will have a telescopic series. There is no such thing, which means that every time, even if the property of telescopicity is hiding somewhere within the sum is there, we need to exercise our wits, creativity, ingenuity, and improvisational skills in order to elicit, in order to expose this telescopicity. That burden is on us. That is why it is fun. It is quite often difficult, and that is why we do these things. There is a pedagogical and educational value in this. And once we understand how these things work, then from middle school we can step up to high school. And in high school you will learn, for example, you can take this further as follows. If we take the limit, if we take the same sum, but this time we will let the summand run from 1 to positive infinity, you see. So then by definition this will be the limit when n grows without bound of Sn, and that will be the limit when n tends to positive infinity of the expression of n over n plus 1, and this will be precisely 1. So this idea, once the idea of telescopicity is understood on the example, on the material of a sum that is finite, we can take it further into more advanced level, into more advanced mathematics. Let the number of terms grow without bound, take the limit, use the expression, compute the limit, and voila, we know that this here infinite sum, or infinite series as some people refer to it, actually can be evaluated as 1. And somewhere along the, let's say, upper high school, perhaps lower college material, the question is, some students often have, why on earth we want to look at this type of sums? And the answer here is that on this channel at some time in the future we will deduce the following. Well, once you guys understood this idea, this manipulation is straightforward. This is infinite series 101. Once you understood this, we can take this slightly further from middle school to high school, from high school to lower undergraduate material. At some time on our channel we will deduce the following formula: 1 over p times p plus 1 times, and so on, p plus n. So this is basically a more generalized, term shown over here, right? Think about it. This is a specific version of this, and this is more general version of this. And how can this be represented? Well, one advantageous representation of this reciprocal product shown over here is the following: 1 over n factorial, integral from 0 to 1 minus x to the power of n, x p minus 1 dx. We will deduce this formula, and that formula actually comes in quite handy when we begin summing these things. When we begin summing these things, this here integral comes handy, and that is why we study these type of sums. And now that we understand more or less how sums that are telescopic work, let us try to elicit the telescopicity of the given finite trigonometric sum next. One of the reasons why on this channel we will be going through this particular exercise many times, we will fix one problem and then try to generate as many distinct enough solutions for that problem in physics, computer science, or mathematics, is because precisely every time when we try to synthesize, discover, generate, create, come up with a new and distinct enough solution, we have to precisely do what mathematicians do when they act in their professional capacity. That is, think out of the box, as declared in the banner of this channel, and face an open-ended problem, rely on their own creative juices, showcase and exhibit their own creativity, ingenuity, and improvisational skills, precisely because there is no, that does not exist a cookie cutting method or template onto which this particular current problem can be laid on top, and then boom, voila, magically we obtain a solution. And specifically, when we look at a given sum, and in this case, let's say we will designate our finite sum with the uppercase C for the trigonometric function of cosine. Cosine begins with C in English, so C here it is. It will be also in some most general sense a function of two arguments, 2, a constant real number A, and a real number theta over here. Then just by looking at the structure of the terms of this sum, how do we know which consequent maneuver will allow us to come up with a perhaps computationally maybe less intensive algorithm or a closed form formula for that sum? We do not know. This is precisely why we do this type of problems on this channel. Because in this case we're facing an open-ended problem, and our creative juices is the only thing we can rely on. At first, if you are new to this, you will feel very uncomfortable, and if you feel uncomfortable, that is actually in some sense good, because you're trying to do the right thing, and in some sense it is bad, because that means that you were never taught mathematics correctly. But this is how mathematics works in general. Yes, the underlying material will change from triangles, straight lines, points, and cosines to spherical functions. For example, field extensions, analytic continuation, quadratic residues, nonlinear differential equations and partial derivatives, kernels of group homomorphism, on and on and on. But the underlying glue, the fact that mathematics is generation and regeneration of ideas, is that fact will remain one and the same. So here we exercise our creativity using elementary material, so that when you step into grown-up mathematics, you will bring these habits with you. So if you are trying to solve this problem correctly and on your own, then this right here, this is precisely the time when you will be doing mathematics. You will be putting your mind into a state that is, in highbrow terms, isomorphic to the state in which the mind of a practicing mathematician operates. And you will be searching for a way to solve an open-ended problem. You will be basically engaging in a cycle of try, fail, try, fail, try, fail. Eventually, if you succeed, you may come to the following idea. If we cannot right away see that our finite sum over here is naturally telescopic, for example, how do we take this guy and represent it as a difference of two modified terms, which when are summed cancel in bulk? Then perhaps we can do a clever manipulation or transformation of the sum itself, or shake the sum in such a way that the shaken but not stirred terms of the new slightly modified sum will exhibit the property of telescopicity. Again, put the video on pause, think on your own, walk away, come back and compare your ideas to ours. Here's one idea. We will use the trigonometric identity shown over here. Usually it's shown in a different way, as a product of trigonometric functions of cosine and sine. This difference divided by 2, 1/2, but I moved 1/2 to the left-hand side of the equal sign over here too. It's just more straightforward that way. We don't have to futz with fractions, but the basic idea, and this is where, in some sense, mathematics, the underlying mathematics, lies, generating an idea. Everything that follows an idea is either not mathematics, depending on how strict you are, or less than mathematics. This is where, in a way, the goal is generating an idea. Running down your idea is a different story, and sometimes you need the technical prowess to carry your manipulation and computation through. But this is where the goal is. This is where you, the whole purpose of solving this problem is generate this here idea. The time that you spend searching for this idea is a time well spent, and during that time you will be doing mathematics. So the idea here is to bring in this here trigonometric identity, which expresses the product of two trigonometric functions, cosine and sine, as the difference. You see, again, we have the difference. In this case, this product collapses into the difference of the one and the same trigonometric function of sine, but the arguments to these two signs over here are different. In the first case, it's a sum, and in the second case, it is a difference. Here is yet another mathematical, if you feel like it, act. One thing is to bring in the idea to use this here identity. Another thing is also is to animate the arguments of the underlying functions with an advantageous material that will expose the telescopicity of the shaken but not stirred given sum. And in this case, we can proceed as follows. The x in this formula over here, in this trigonometric identity, can be put equal to the argument of the given trigonometric function of cosine. So constant real number plus the varying material k times another real number theta will be our argument x in this formula over here, x, and y will be theta over 2. And again, to people who are new to mathematics, actually a good question over here is the following: Roman, why theta over 2? Why not square root of theta? Or why not theta squared over 3 factorial? Or why not arctangent of logarithm of something, some wild stuff? Why theta over 2? Where did this come from? And how can we come up with that idea? This is an excellent question. And the answer to this question is the following. The idea to yank this out of your imagination lies on the other side of, again, the same cycle: try, fail, try, fail, try, fail. And again, it should be understood, and this is probably also one of the reasons why many people will feel uncomfortable, because you were not taught mathematics correctly. No one will hold your hand in mathematics and tell you, follow this cookie cutter template and do this. The burden of inventing this material is on you. So try and fail, combine this trial and failure with the idea that maybe the sum is telescopic, and you will see that eventually this will be a winning ticket. And again, maybe looking ahead a little bit, at some point we will come to this number over here a couple more times in the next episode, when we will be evaluating that sum using complex numbers. We will also come across 2, and in the solution, the solution in the next episode will be algebraic, just like in this one. But in the third episode, the solution will be based on synthetic plane Euclidean geometry, and there we will actually see where does this 2 come from. So for now, as a purely algebraic solution, as an algebraic manipulation, by playing with this identity and the structure of the given sums, you will eventually realize that yes, this here is a winning ticket, and this is how we carry this idea through. Multiply both sides of the given sum by twice the value of the trigonometric function of sine evaluated at the angle of theta over 2. In other words, put 2 sine of theta over 2 on the right hand side of the equal sign under the summation sign, and put 2 sine of theta over 2 on the left hand side of the equal sign. Using the fact that the product to sum trigonometric identity shown over here is valid for all x, y real, and using the fact that in the modified sum we put x is equal to the argument of the trigonometric function of cosine, and we put y as the argument of the trigonometric function of sine, which is theta over 2, begin spelling out all the terms on the right hand side of the modified sum according to that identity as follows. That task is mechanical, so for k equal to 0, we will have what on the right hand side of the equal sign for the first summand? We will have twice the cosine of a times the sine of theta over 2 is equal to, according to our formula that I will keep here for convenience purposes, that will be what? That would be sine of, that would be the sine of a plus theta over 2 minus sine of a minus theta over 2. This is straightforward middle school arithmetic, nothing to it. When k is equal to 1, then for the next term we will have the cosine of a plus theta times the sine of theta over 2 equal to the value of the trigonometric function of sine evaluated at what? a plus 3 theta over 2 minus the value of the trigonometric function of sine evaluated at the difference between x and y, which is what? Which is a plus theta over 2. For k equal 2, we have 2 times the value of the trigonometric function of cosine evaluated at a plus 2 theta times sine of theta over 2 equal to sine of a plus 2 plus 1/2, 2.5 of 5 over 2, 5 theta over 2 minus sine of 2 theta minus 1/2, 1.5, which is 3. Because that task of unfolding the summands of the modified sum shown on the right according to the trigonometric identity product to sum is trivial, and I did not want to bore you guys with watching me write down all these expressions over here. This is a typical middle school task. I already wrote it down for you, and the only thing of note over here, again, there's nothing intellectually challenging over here. All we have to do is be careful when k is equal to n. When k is equal to n, for the very last summand, we just have to carefully write down, unfold the product into the sum here. For the addition to the constant real number a, we will have 2n plus 1 over 2 theta. And when we subtract the sign, it will be 2n minus 1 over 2 theta. Make sure that you guys catch this specific detail, 2n minus 1 over 2, 2n plus 1 over 2 theta over here. And now what do? Remember that in our little bit of theory, the original sum did not seem to be naturally telescopic. By multiplying both sides of that sum by this expression over here, we obtained our uppercase AK. Remember, this is uppercase AK, and this uppercase AK got decomposed into lowercase AK like this. Here we have the difference, and the difference. And what do we see now? Well, now we witness the fact that the modified, not the original sum, but the modified sum, and that modification over here, again, it is an open-ended task. If you feel uncomfortable figuring out or understanding where did it come from, in some sense, this is a good thing. You're trying to learn, you're trying to do the right thing, and this is how, in general, mathematics operates. The burden of synthesizing a line of reasoning is on U. This is what mathematics is about, not just raw symbolic shuffling. What we're doing here specifically is either not mathematics, it's more of a computational calisthenics, but we're trying to validate our idea. This is where the idea was. So now we're witnessing the fact, our idea, and this is where mathematics is manifested, was to bring in this identity, set X, set Y, perform the calculations, and now we reap the benefits and we collect the harvest of good things. What do we see? Well, we see that, what is it? Northwest to southeast, this way, look at this. This summand enters into the sum with the plus sign, and the like summand, exactly like summand, enters into the sum with the negative sign here. They cancel each other out because remember, our sum, the original one, and then when it's modified, becomes equal to the sum of all these expressions, this plus this plus this plus this plus this. When we sum, what do we witness? Well, these terms cancel out. 3 theta over 2, 3 theta over 2, excuse me, cancel out, cancel out. 5 theta over 2, 5 theta over 2 with a negative sign, cancel out, cancel out. And you can see that eventually 7 theta over 2 will cancel out with its image with a negative sign. So that means that this summand over here will cancel out. And what do we see? Well, exactly things worked out according to our definition when and if each and every summand of a given sum can be represented as the difference in such a way that when all these new modified terms are added together, the bulk of them cancels out. This is precisely the template of a sum that is telescopic. We see that the modified sum is indeed telescopic. And what survives? Well, let's highlight it with blue. The only terms that survive this perfect storm of cancellation is the first summand of the last difference and the second summand of the first difference. These are the only survivors of this here cancellation process. And now that I will take a second to erase this, all this intermediate material and show an intermediate result, that result will look as follows. Here, to save you guys some time, I erased all the intermediate calculations. I captured on top the result that we obtained through witnessing the telescopic effect of terms in the modified sum canceling each out in the northwest to southeast fashion. These are the two terms that we obtained, and in some sense, some of our viewers may say, Roman, this is already as good of a closed form as it gets. We have our sum Cn. This is a multiplicative term that sits in front of it that can be carried under over here, and voila, we have it. The answer is yes. Of course, by all means, we can leave it like that, but for the reasons that I will explain in a few small number of minutes, we like to execute the following middle school maneuver. We want to go the other way around and transform this sum into a product, and we do that by using our popular middle school identity, which holds for all x, y real. We do not prove these identities for now. In this episode, we take them to be already proven. So for all x, y real, the difference between the values of the trigonometric functions of sine evaluated at x and at y is shown over here. It's twice the cosine of half the sum and sine of half the difference of the original arguments. And in this case, we evidently put x, y, this is all trivial stuff, x, y, we compute the sum, x plus y is 2a plus n theta, a and a 2a, 1/2 theta and 1/2 theta cancel each other out, 2n over 2 is n, so here we have n, elementary, x minus y, the difference, a and a cancel each other out, and what over here, negative times negative becomes positive, so we slug in another copy of theta over here, 2n plus 2. 2 factor out, 2 in denominator, 2 in the denominator cancel each other out, n plus 1 remains, bam, n plus 1 theta, and according to this formula, our modified sum is expressed as twice the product of the trigonometric functions shown over here. And what do we see over here? Oh, look at this, what a miracle. 2 and 2 cancel each other out, and voila, we have our Cn in closed form, in which we precisely compressed the sum of all the terms of all the summands into a product, and we can write it down as follows. And if we write the result neatly, then we will have the following: the finite sum of the trigonometric functions of cosine, the argument of each of which is in the following arithmetic progression: a constant real number plus k theta, where theta is a real number, and k varies from 0 to n, where n is a non-negative whole number, can be represented as the following product: the value of the trigonometric function of cosine evaluated at a plus n theta over 2 times the following ratio. In the numerator, we will have the value of the trigonometric function of sine evaluated at the argument n plus 1 over 2 theta. And in the denominator, we will have the value of the trigonometric function of sine evaluated at the argument theta over 2. This is theta over 2, n plus 1 over 2 times theta, a plus n times theta over 2. This is the final result that we were looking for, and that formula can be used in a number of different ways. The regular viewers of our channel, especially those of our viewers who have studied the problem-solving approaches with us in a dedicated manner across Season 1 and Season 2, should instantly recognize what? They should instantly recognize the so-called reduce and conquer. Reduce and conquer. Reduce and conquer is another problem-solving approach that is in our toolbox right now, that is in our problem-solving arsenal. So now we take all the heavy lifting, all the hard work that we did while deducing this formula, and this is how things work in general in other areas in mathematics, in the theory of groups, theory of graphs, in real analysis, complex analysis. We do heavy lifting and hard work in one case. In similar cases, we do not really fight the same fight. We try to offload all this computationally intensive work to a clever maneuver, and that clever maneuver in this case comes in the guise or in the shape of reduce and conquer. We use the following identity that says that for all x real, it is the case that the cosine of pi over 2 minus x becomes the sine. We can even visualize this graphically by shifting one graph into another. But the idea here is the following: hijack this identity and then uniformly replace a with pi over 2 minus a and theta with minus theta. In this result, all the way across, uniformly means here, 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 and here. When we do that, we will have sine of minus something. The sine is a function that is odd. Factor out minus. Here is minus in the argument. Factor out minus. Minus and minus cancel each other out. Here, this argument becomes precisely pi over 2 minus a plus k theta, and this is how we synthesize the formula over here. This is the finite sum for the trigonometric functions of sine, each argument of which is in the same arithmetic progression as over here, a plus k over theta. And we see that if I were to rewrite this suggestively, this is not just some random portrayal of this formula. This is my idea, guys, because there is a small quiz lurking in the middle of this. try to think to compare, juxtapose these two formulas one against the other, and try to think if you see anything peculiar. Put the video on pause, think on your own, walk away, come back and compare your idea to ours. There is a peculiarity over here. We can see that either way these formulas can be expressed as sine of something times a common ratio, and then cosine of something times one and the same ratio. Look at this. These two terms that form a ratio in the formula for the cosines is exactly the same as the two trigonometric functions of sine. They form the same ratio for the sum of sines. So what is going on over here? Do you have an explanation? Plus, why all these halves? Where do all these halves come from? Why do we see 1 over half in all these formulas? Think on your own, and we will proceed as follows. I will share, again, put this video on pause, walk away, think on your own. I'll give you a hint. I will explain this peculiarity that sine times something, cosine times the same thing, using synthetic Euclidean geometry in the episode that will come after the next one. And here we can exploit these two formulas in a number of different ways. For example, we can put a equal to 0, set a equal to 0, collapse the sums accordingly, and obtain a result. We can also do next what? For example, instead of rolling the sums with 0, especially in the sign, once we set a to 0, when k runs from 0, the first term will be 0. It's not interesting. So after setting a to 0, we can set k to 1, and obtain the corresponding results, modify the results over here. But this is in some sense trivial reductive work. And this is just to show you guys that in mathematics, it is possible sometimes to carve multiple distinct paths to one and the same result. So here we obtain this result using one of our favorite problem-solving approaches called reduce and conquer, because here this problem is a reduction of the obtained result. Here we obtain this result instantaneously, almost. There was zero work. Set, use, write down, done. No intellectual effort virtually. But if you want to exercise your understanding of how telescopic series or how telescopic sums work, then my suggestion for you guys is to go through the same motions and obtain this here result, this formula, by using precisely the notion of the sum that is telescopic, and in the compressed way. I will not go into all the gory details as I did with the cosines. In the compressed form, this deduction that reveals the underlying telescopicity of an appropriately modified sum of sines will look as follows. Again, it may be a good idea for some of our viewers to use this little segment as a way to practice mathematics correctly, as we explained in Season 1, Episode 2. And if you did not understand this or that aspect of our previous explanation and you're still not sure how to proceed, watch only bare minimum information that we present, and as soon as you understand what is going on, put this video on pause, walk away, and carry the resultant computation through all the way on your own. As such, here we begin. We write down the expression for our finite sum Sn for the values of the trigonometric function of sine, each of which is evaluated at the argument that is in the arithmetic progression a plus k times theta. And then we multiply both sides of that equality by twice sine of theta over 2. On the right, this factor gets glued to each and every summand of the original series. Here we have it by itself. Then we use the following product to sum identity that holds for all x, y real, and we use this identity in order to spell out the terms of the modified sum on the right hand side by looking at each summand shown over here, this guy. Once we write these terms down, this again a straightforward computation. On the left hand side we will have the original product when k equals 0, k equals 1, k equals 2, and so on, k equals to n. We spell out each such product as, in this case, advantageous difference, 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 difference. Write it down. The arithmetic is straightforward. Then what do? Well, we witness the fact that we are able to unfold or transform each and every, remember from our theoretical segment, uppercase A sub k as the difference of two modified, not the original, but modified terms in such a way that when all these terms are added together, the bulk of them cancels out. And what do we see in this case? Well, in this case, instead of northwest to southeast as it was in the previous segment, now we see the cancellations, parabolically speaking, taking place from northeast to southwest, this way. Look at this. Cosine of a plus theta 2, cosine of a plus theta 2. Here we have a plus 3 theta over 2 in the northeast, and in the southwest we have this guy, a plus 5 theta over 2 in the northeast, and then so on, and eventually this term will also cancel out. And what terms will survive? Only the first modified term of the first difference in the last modified term of the last difference with the negative sign. Don't forget we have the negative sign. Pull up a new sheet of paper, write down the result correctly. When we sum, plus, 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 cancel, 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 boom, plus sign. What do we have in the bottom? At the bottom we will have only two standing terms, the cosine of a minus theta over 2, the first term, and the last term over here, cosine of a plus 2n plus 1 over 2 theta, 2n plus 1, pay attention here, 2n plus 1, and this is a plus, this is a minus. And now again we go back. At this point we can drop it on the floor cold turkey and say boom, done, walk away. In some sense, yes, this is a legal maneuver. We marry this guy to this guy and we have our S of n. But for the reasons that I will explain in the next segment in a few seconds, it is nice to convert or collapse this difference or sum, if you will, in general, into a product using this here middle school identity. For all x, y real, it is the case that the difference between the values of the trigonometric functions of cosine evaluated at the arguments x and y is shown over here. There is a minus sign over here, guys. Don't forget, don't overlook this. Minus, 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 alert, alert, alert. Here we have it, sine of half the sum and sine of half the difference, x minus y over 2, xy plus over 2. We put x equal to a minus theta over 2, the first argument of the cosine, and we put y equals to a plus 2n plus 1 over 2 theta, the argument for the second cosine. Again, I do not want to insult your intelligence. This is just as a checkpoint or a reference with the correct response. This is not even mathematics. This is computational calisthenics. You're expected to snort this with your left nostril and roll through it. X plus y is 2a plus n theta. X minus y is negative. See here again, guys, pay attention, negative n plus 1 theta. And what do we do now? We put the half sum, half difference back into this formula, and we have negative 2 sine of a plus n theta over 2. And then we take the sine of this. Sine is the function that is odd, so minus here comes out, collides with this, minus 1 times minus 1. Oh, what a miracle, plus 1, the negative signs disappear, and what survives? What survives is the sine of twice the sine of half the sum, is this guy, and the sine of half the difference, which is this guy with the positive sign here, this guy. And 2 and 2 cancel each other out, and voila, we have our formula. This is our result. And we again remember that we obtained this result. Not by using the reduce and conquer as we did previously, almost instantaneously in 3 seconds or less of effort. Here we put some work into it, yes, but this is a good way to work out your understanding of how telescopic sums and series work. And now a few words about the application of these formulas, and I will try to answer a very popular question of why are we evaluating the sums. Concerning the practical side of the results that we achieved or the results that we deduced, here is the deal. We have our formula for the finite sum of the trigonometric functions of cosine, the arguments of each of which are in the arithmetic progression shown over here, the same finite sign for the sines, for the trigonometric function of sine. And now what happens, as I said before, we can try to manipulate these results into various shapes. For example, one such manipulation I already mentioned: put a equal to 0 in both formulas, write down the results, and now after that start rolling k not from 0 as shown over here, but from 1. The results will be obtained and expressed accordingly, because trigonometric functions um, afford all sorts of alternate ways to express them that can be shown in a number of ways, but this is basically the idea. The other angle of looking at this here formulas is the following. I wrote for you guys over here on your own as an informal baby mathematical research. What I can suggest to you guys is, right now, look at this. Our dummy summation variable k in both cases varied uniformly, so to speak, without any gaps or interruptions. K equals 0, 1, 2, 3, 4, 5, and so on. Here, try to experiment on your own with the sums where the argument, let's say, forget about a, throw it out, it doesn't really matter. Let's put a to 0. Experiment with odd multiples of the angle theta, odd multiples, 2k minus 1 times x, for example, and even multiples of x, or theta, if you will, 2k theta, 2k minus 1 theta. See how the dummy summation variable k has to vary, but that's the idea. Investigate the sum of the cosines when the angle is an odd multiple and when it is an even multiple of the real number x or theta or whatever. See what kind of results you will produce. On the one hand, this is a good exercise to see if you can splice your understanding of telescopicity. Maybe you can reveal the telescopic nature in this formulas. On the other hand, also in addition to it, see if you can fold these formulas over here into the corresponding results by using reduce and conquer. And to give you an example of why these things are done, here is, I showed, for probably for some people this will be a scary result, but the deal here is the following. This is, depending on your course, I think in my time I took it, that was my 1, 2, 3, 4, fifth. It was my fifth semester. That was the first semester of year 3. First semester, third year, Fourier analysis. Here's Fourier analysis. So here is Fourier series decomposition of the function e to the power ax over the subset of real numbers, minus pi pi, not inclusive, not inclusive. So here it is, 2 over pi, hyperbolic sine of a times p, and the squiggly over here runs from here to here. All this material is multiplied by this factor over here, 1 over 2a plus the sum. This is a horrible expression over here, a squared plus n squared in the denominator, minus n to the power of n in the numerator. And the factor to over here, these are the Fourier coefficients over here, a times cosine n of x and minus n times sine n of x. These are our Fourier coefficients, and this is it. We compute all sorts of integrals. We put our back into it. We do the heavy lifting. We bite the bullet and say, okay, let's do it. We do it, but now what happens? Look, what happens next? Well, once we have this decomposition, just like over here in the toy middle school case, in the higher brow grown-up mathematics, we say, okay, uniformly replace x with minus x. So walk through these formulas, step, 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 thump, 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 x minus x, x minus x. Look at the result, write it down, and then add to this decomposition, Fourier series decomposition, the result for e to the power of negative x, divide by 2, obtain what? Obtain the Fourier series decomposition of the hyperbolic cosine almost instantly on the chip with no effort. Subtract from this the decomposition of e to the power minus x divided by 2 and get what? The decomposition of the hyperbolic sine. Also, again, reduce and conquer in action in the highbrow academic setting. There you go. But leaving this aside, this idea of manipulating this results in various ways, in various directions, by setting certain material to 0, by varying the quality of the dummy variable, not just 1, 2, 3, or odd, even, maybe y the step. Experiment, research, see what happens, and use these formulas as a checkpoint. If you do this, mechanically this, but then if you put some intellectual effort into it and touch all these intermediate steps by hand, this is the result. Do they agree? Yes, wonderful. The other angle over here is this. Later on in your career, you may be asked to compute, for example, this integral from 0 to pi over 2 of sine of 2k minus 1x. You may recognize my argument over here. This is a suggestion. This is a suggestive notation, and then this guy divided by sine of x over dx. What is this integral? Well, on the face of it, it looks quite scary because signs in the denominator usually do not promise anything good. But if in this formula we recognize some of this material here, look at this. Product reversed into the sum, and sum can be integrated trivially. There you go, finite sum. You do not need to worry about uniform convergence. None of this is relevant. Boom, mechanical effort. Or how about this integral, for example, from 0 to pi over 2 with square. Look at this square, a similar ratio, but here sine of n of x divided just by sine of x. And all this mess is squared. Integration is carried out over with respect to dx. Give. Again, in these results, you should be able to recognize some of the material. This will be sitting on the receiving end of your research, baby mathematical research that you'll be doing with these formulas, and this will help you down the road with even more higher brow mathematics. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you guys. This will be a mathematical problem S3E3. And in that solution, in that episode, I will show my solution, my algebraic solution of the same problem. We'll obtain these two results shown over here, the same two results, but we will use the wonderful power, tactical power of complex numbers instead.